For this talk, I'd like to discuss another metric that criticizes or a loss function for regression models, that is, models that predict a number. Now, the idea is if yi is the ith value we're supposed to predict, and vi is our ith prediction, as I've said in an earlier lecture, we very much want them to be close in the sense that the SSE, which is defined as the sum over all examples, suppose we have n of them, of yi minus vi squared is minimized. And this is a great loss for regression and numeric prediction functions. However, it has two flaws as far as humans are concerned. Computers deal with this just fine, but the two flaws are, which we discussed in our earlier talk, is this is in unnatural units. If yi and vi are dollars, then this is dollars squared, which is a strange unit. And this is not normalized in the sense that larger data sets have higher SSEs. So that depends on the data set size. So if you hear an SSE of 1003, you have no way of knowing whether that's large or small, even with your domain knowledge of what sort of numbers you were working with. So that's a bit of a problem. So the way we normalize that is, well, one way we said is the root mean square error, which is just 1 over n SSE square root. So we divide the SSE by how many rows to get the average square difference per row, and then we take the square root to knock that back into natural units. And so the RMSE is just how much your prediction is typically off in a typical row. So that's a really nice quantity. It's just there's another normalization which is also of use. And I'm going to be a bit abusive here, but only for defensive reasons. So basically, the other metric that's really useful, I'm going to call the R squared. And I'm using this backwards R for very specific reasons, and which I'll get into in a little bit. But the R squared is defined as, and again, I can define it however I want because I've done my own. It's essentially the 1 minus sum I equals 1 to n of how bad is our prediction divided by I minus OI squared. So OI is another prediction, and we hope our prediction is better. So that means we hope that this fraction is small, that our numerator is much smaller than the denominator. Therefore, this small number subtracted from 1 is very close to 1. So R squared of 1 is great. And R squared of 0 means that our model is of the same quality as the other model. The numerator equals the denominator. And R squared can be negative, which means our model is much worse, because that means this fraction exceeded 1 because the numerator was much larger than the denominator, and this number larger than 1 got subtracted 1. So negative means we're worse than the other model. So it's a formal comparison of models, and the traditional thing we plug in here as the competing model is just y bar, which is defined as the average of y. So the traditional R squared is, are we better than just guessing the average for every single individual? And that's a really compelling difference to check, because if we're going to treat everything as indistinguishable, i.e. not use a model, well, that's roughly equivalent to just using the average, whatever that may be, as the average prediction for everyone. So it's basically our model that's subscripted and changes its prediction per example. Is that better than the best possible model that's not subscripted, guessing the grand average, which is, for square loss, the best possible guess if you're not going to change your guess per row. Now, why are we talking about this with this stupid backwards R? It's basically for this reason that R squared in statistics is only on training data. Which I think is a horrible loss, because this is actually a really good function to master and evaluate. And also a bit of a lie, because if the traditional R squared is only for training data, why do they estimate the adjusted R-squared to try to get the number of model degrees of freedom out? Because they want to know how the model will perform in the future, what R-squared would be expected on new data. So it's a bit of a lie. It's, to be a bit crude about it, is basically, this is Alice in Wonderland grade stuff, where Humpty Dumpty says, when I use a word, Humpty Dumpty said in a rather scornful tone, it means just what I choose it to mean, neither more nor less. So statistics is a mathematical field that tries to model how empirical things happen in the world, subject to noise and uncertainty, and that basically they're sort of unconvinced about the mathematics of the backwards R-squared, that, hey, this formula works very well, even on non-training data, and they're also unimpressed by the empiricism that you actually make very good choices using this metric even on test data. Now, a number of nice properties of this R-squared are lost. For instance, on training data under fairly mild conditions, the R-squared is the square of the correlation. Dr. Nina Zimmel has an article saying when that's true. There's actually some technical conditions required to do that. And so yeah, that's a nice property, but it's not the core. So I kind of like this R-squared. I use it a lot. And the other question is, which I think is a brilliant question, is what mean or other model should you compare yourself to? Is this Y bar for the training data or Y bar for the new evaluation data, which is much stricter, harder to beat? And that really depends on the application, I think. So in finance, for instance, even knowing this average over future data would be incredibly valuable. So that means you maybe evaluate with respect to the mean you took on your training data to see if you're better than using that grand mean going forward. Or if you really need to make decisions that are better than treating everything the same, then you use the mean on the test data, because treating everything the same treats everything as if it's the mean without needing to know that mean. So even though you may not know the mean on the future test data, it's an interesting number to plug in for comparison. I think basically any distinction between these two numbers is either a joke, like I'm doing here, or bullying, as I actually see quite a lot on the internet. And basically, in empirical sciences, which data science is an empirical science, we don't so much care what something was designed to do or what the brand name was. We care about what it can do.
I don't care what anything was designed to do. I care about what it can do.
So thank you very much for your time. Please do not reproduce this distinction, but just know when you use R-squared, there are some criticisms of it. I think actually in practical terms, it's a really great metric that it should be used all over the place to great success. Thank you very much.